Hello everybody, we are on notes number 7 today, and we're going to talk about inverses, and then we're also going to talk about properties of exponential and logarithmic expressions, solve exponential and logarithmic equations, and talk about the functions a little bit. So today has a lot to do with all things exponential and logarithmic. But first, let's talk about inverses. And you have learned some different things about inverses that we could categorize as graphical, numerical, algebraic, and algebraic. So what do we know graphically about inverses? Here's an example. Let's say we have an exponential growth function, and let's say we have the line y equals x. The inverse is going to be the reflection of that function across the line y equals x. So roughly something like this. So what we know is that inverses are reflections across y equals x. That's the graphical characteristic. How about numerically? Well, if I go back to that graph, and let's say this point here was the point, maybe 2, 5, then on the inverse, we're going to have the point 5, 2. The x and y coordinates switch. So we could say that if the point AB is on function f of x, then the point BA is going to be on the inverse. Remember, the notation is f inverse of x. And that's the notation we would use if they're both functions. Algebraically, what do we know? Well, one of the things we know algebraically is that because inverse operations undo one another, like multiplication undoes division, addition undoes subtraction, squaring undoes square rooting, what happens if you have one function inside its inverse? So if f of x and g of x are inverses, if you compose them, so function composition, f of g, g of f, then the inverse functions are going to cancel. The inverse operations are going to cancel. So f of g of x is just going to be x, and g of f of x is just going to be x. And then also algebraically, what we can do as our method for finding an inverse, so how to find an inverse. The process is to take the function and call it y if it's not already called y, and then switch x and y. Sometimes you see the word switch or the word interchange, and then isolate y or solve for y. And then you can rename it like f inverse or g inverse, whatever letter you were using. Okay? So, for example, if you had f of x equals 3x minus 4, and you wanted to find the inverse. First, you could call this y equals 3x minus 4. And then your first step in finding the inverse is to switch x and y. So the inverse is x equals 3y minus 4. But we typically don't leave it like that. We typically will then solve it for y or isolate y. So we can add 4 to both sides and divide both sides by 3. You could write it like this, or you could divide each term individually by 3. And so that is the inverse, and then we can rename this f inverse of x. You could write it as 1/3 x plus 4/3 if you wanted to. And if you had to graph it, that would probably be the way to go. Okay, now your calculus book uses a term that we didn't use in pre-calculus. The term is invertible. It's kind of intuitive what they mean. To be invertible means that the inverse exists. Now, different mathematicians have different criteria for determining if the inverse exists. In your book, for the inverse to exist, so for f of x to be invertible, f of x must be 1 to 1. So what does that mean? That means every x coordinate has only one y coordinate, and every y coordinate has only one x coordinate. So, in other words, it passes the vertical line test and the horizontal line test. Let's take a look at a little example here. Let's say we have something like this. Oh, let me do that again. Okay. The vertical line test. For every x coordinate, there's only one y coordinate. A vertical line is only going to pass through one point. So this passes that test. The horizontal line test. For every y coordinate, there's only one x coordinate. Every horizontal line I draw passes through only one point. So this passes that test. Every x has only one y, every y has only one x, so this is invertible. Now, some mathematicians say that the inverse only exists if the inverse is a function. And the way for the inverse to be a function is for the original to pass the horizontal line test. Therefore, when you invert it, you pass the vertical line test. So this would mean that f of x must be 1 to 1. That's another way of writing 1 to 1. Instead of writing words, just use the number. This school of thought is f of x must be 1 to 1 for the inverse to exist. So for it to be invertible. Okay, that's the position that the mathematicians who wrote your book will take. On the other hand, some people will say that the inverse does not have to be a function. So an example of that would be if you started with, say, this f of x, which is a function, but then if you reflect it across the line y equals x, you're going to get something more like kind of like this, I guess. That's not exact, but more or less like that. And that's the inverse, but it's not a function. It fails the vertical line test. So our book's authors would say that inverse does not exist. Other mathematicians would say, well, it's an inverse, it's just not a function. Okay, so some mathematicians would say this is an inverse. There are other things like that in math where mathematicians just don't happen to use the same definition. That doesn't bother me too much. It might bother you. I don't really have a preference one way or another. I'm just going to kind of follow along with what your book does because that will make it easier to use the answers and the problems that are in your book. Okay, so that's a lot of information about just the concept of inverses. Let's do an example, a couple of examples. What about is f of x equals x squared invertible? So according to the authors of your book, is it invertible? Does it have an inverse? Well, let's see. Is it 1 to 1? There are different ways we could figure it out. The easiest for this one would be to visualize the graph of f of x equals x squared. It's just a parabola opening up with vertex at 0, 0. It fails the horizontal line test. So it's not invertible. Now, for the next example, let's say we take the same function, but we restrict it to only a domain of x is greater than 0. So let's take a look at that. We're only going to take that part of the parabola, not the whole thing, just a piece of it. Is it 1 to 1? Well, it does pass the vertical line test, and it does pass the horizontal line test. So yes, so that means it is invertible. meaning if you were to draw the inverse, it would pass the vertical line test and it would be a function. Okay, let's switch gears now, and we're going to focus specifically on exponential and logarithmic things. Exponential and logarithmic expressions, equations, functions, although I think we did touch on exponential and logarithmic functions already on the day we looked at different classes of functions. We looked at how exponential growth looks like this, or exponential decay goes downward. We looked at how exponential functions have a horizontal asymptote, while logarithmic functions, which are their inverses, have a vertical asymptote. So we won't go into all the detail about those again. Let's focus instead today on how we simplify expressions and solve equations. Okay, this is a picture of your book, which was really a picture. So this is quite fuzzy. You can look in your own book, it'll be a little bit less fuzzy. But these are the properties or laws of exponents that you've been using for years, ever since Algebra 1 or maybe even pre-algebra. So we have the product property. We use that at times when we do something like this. 2 to the 4th times 2 to the 5th is 2 to the 9th. We add the exponents. Okay, that's using the product property. We have the quotient property. Oh, look, there's examples right there. I don't have to make up my own. We have the quotient property, 4 to the 7th over 4 to the 2nd. You subtract the exponents, you get 4 to the 5th. We remember that negative exponents mean reciprocal. So if you see b to the negative x, you make it 1 over b to the x. If you saw 3 to the negative 4th, you make it 1 over 3 to the 4th. And we have the power property. So if you raise a number to a power and then you raise it to another power, you have to just multiply those exponents together. Because if you add 3 squared to the 4th, it would be 3 squared times 3 squared times 3 squared times 3 squared, and when you add all those together, you have 8. You have 4 times 2. Okay, so the shortcut is just to start by multiplying the 2 and the 4. And we also remember that when we have rational exponents, like fractions as exponents, those indicate roots. 5 to the 1/2 power is the same as the square root of 5. Okay, so I think I've talked about all of these. Now, I don't know why I didn't say anything about the top one, but hopefully we all remember that a 0 exponent means we just have 1. So b to the 0 is 1. Not 0 to the 0, though, but any other value of b, like 1 to the 0 is 1, 2 to the 0 is 1, etc. Okay, now let's also review our logarithm laws of logarithms, or properties of logarithms, which are on page 46 of your book. And we spend a lot of time in Algebra 2 and pre-calculus talking about the product property and the quotient property and the power property of logarithms. So I would suggest you take a look at those examples as well and make sure that those ring a bell for you. If you have something like this, log base 5 of 5, what that means is you're going to take 5, the base, raise it to some power. That's what goes over here, the power, and you'll get a result of 5. So 5 to what power gives you 5? 5 to the first power gives you 5. So that's the log of b law there. And what if you have log base 5 of 0? Nope, not 0. Log base 5 of 1. That means you take your base 5, you raise it to some power, and the result is 1. 5 to the 0 power is 1. Remember, that relates back to that exponent of 0 law. All of these logarithm laws relate back to the exponent laws. Okay, every once in a while we use a logarithm law in calculus. Not that frequently, to be honest. Okay, what I want to do next is just work through some examples where we're simplifying expressions using exponent properties. And we don't need to grab a calculator for this. I want to make sure you can see how the properties will work so that you can do them even without a calculator. If you have 27 to the 4/3 power, that's equivalent to 27 to the 1/3 to the 4th. Okay, power to a power. And 27 to the 1/3 power means the same thing as the cube root of 27. The cube root of 27 is 3. So we have 3 to the 4th. And 3 to the 4th is just 81. So that expression simplifies to 81. Here's the next one. 8 to the negative 1/3 power times 8 to the 5/3 power. Now because both of these have a base of 8, we can add these exponents together. Negative 1/3 plus 5/3 is 4/3. So we have 8 to the 4/3 power. Hey, now it's kind of like that previous one, something to the 4/3 power. So let's break that up into 8 to the 1/3 to the 4th. And 8 to the 1/3 is the cube root of 8, so that's 2. And 2 to the 4th is 16. Okay. The next one, we're just combining various operations together to make a more complicated problem. So let's see here, what can we do? So we have 3 times 4 to the 1/4 minus 12 times 2 to the negative 3/2. Notice that this one has a base of 4 and this one has a base of 2. Actually, 4 is a power of 2. So what if we work to get both of these to have the same base? So 4 is 2 squared. I'll just leave this one for now. We don't know what's going to happen just yet. 2 squared to the 1/4 would be the same as 2 to the 1/2 if you multiply those powers together. And if you have a negative exponent, you can change that into the reciprocal. So we have 2 to the 3/2 on the bottom instead of 2 to the negative 3/2 on the top. I'm thinking if I do more, somehow these might combine. I'm trying to figure out if they will. So let's see. Let's keep this as 3 times 2 to the 1/2. We could also think of that as 3 times square root 2. I'm going to do that. 3 times square root 2 minus 12 over, now you can think of 2 to the 3/2 as the square root of 2 cubed. That would be the square root of 8. Square root of 8 is 2 square root 2. Oh, now we're getting somewhere, because if we rationalize that, and if we reduce it, we can just make that a 6. If we rationalize it by multiplying the square root of 2 over square root 2 by that to get rid of the radical on the bottom, we're going to have 3 square root 2 minus, notice we have 6 square root 2 over 2. And we can reduce the 6 over 2, make that a 3. Oh my goodness, this is 3 square root 2 minus 3 square root 2. This is just 0. Who knew all of that was just a special form of 0? We just had to persist and keep doing things. We did different kinds of things. Exponent rules, other exponent rules, change to a radical, rationalized denominator. All that led us to 0. All that for nothing. Okay, let's simplify a few log properties, or log expressions using log properties. Again, we can do these without a calculator. Just keep this in mind. 5 to what power would be 1/25? How about 5 to the negative 2nd power is 1/25? Because we know 5 squared is 25, so the reciprocal of that would give us our negative exponent. So this expression is just the same as negative 2. And there are also different ways to get to it, like if we use the quotient property of logarithms, we could break this into log base 5 of 1 minus log base 5 of 25. Log base 5 of 1 means 5 to what power is 1? That would be the 0 power. Log base 5 of 25 means 5 to what power is 25? That would be 2. And 0 minus 2 is negative 2. So we get negative 2 either way. All roads lead to negative 2. Let's try this one. Log base 2 of 8 to the 5/3. Again, there are lots of different ways we can do this. One way is we can use the power property of logarithms, which says if you have a power here, you can bring it out to the front and multiply by it. So we have 5/3 times log base 2 of 8. What's log base 2 of 8? 2 to what power is 8? 2 to the 3rd power is 8. So log base 2 of 8 is just 3. 5/3 times 3 is 5. There are other ways we could do that as well. Okay, here comes a sum of two logarithms. Let's see, what can we do here? Well, 30 is a product of 5 times 6, so we could think of this as log base 25 of 5 plus log base 25 of 6, using that log property that says you break up the product into a log plus a log. This is a quotient, so we could break this one down into log base 25 of 5 minus log base 25 of 6. That's the quotient property of logarithms. I think that helps because we have plus log base 25 of 6 minus log base 25 of 6. So let's cancel those. And what do we have now? We have 2 of these. By the way, 25 to what power is 5? 25 to what power is 5? Well, isn't it the square root of 25? That's 5. So what power would that be? The square root is the 1/2 power. So this is actually just 1/2, and we have it again 1/2, and the answer is 1. All that is just equivalent to 1. Who knew? Okay, we're getting close to the end here, I hope. Now we have 8 to the 3 log base 8 of 2. Well, did you know that if you have 8 to the log base 8 of, let's say, star, it's just going to be equal to star because inverse functions cancel. 8 to a power is the inverse of log base 8. They're going to cancel, leaving you with just star. So we almost have that situation here. What we can do is use our power property and bring this 3 up and make it a power on 2. So now we have 8 to the log base 8 of 2 cubed. There we have 8 to the log base 8. Those are going to cancel, leaving us with just 2 cubed. By the way, what's 2 cubed? 8. So our answer is 8. Okay, I know we have a little bit more to go. This is going to be a long video today. We're going to solve a few equations. So exponential equations. If you have e to a power equals e to a power, those powers are going to be equal. So you can say that t squared equals 4t minus 3. Then we'll solve that equation. Since it's quadratic, let's get everything over to one side, set it equal to 0, and if possible, factor it. I think it's going to be possible here. And then we'll set each factor equal to 0 and solve each one. And we're going to get t equals 1 or t equals 3. Okay, this next equation is actually not exponential. See, to be an exponential equation, your variable has to be in the exponent. But in this equation, the variable is in the base. It's not an exponential equation. We can still solve it. What we can do is take the 4th root of both sides because we have a 4th power there. So if we take the 4th root, just like if you were to take the square root of both sides, you actually need plus or minus. So b equals plus or minus the 4th root of 10 to the 12th. Now couldn't we think of the 4th root as a 1/4 power? So this is the same as 10 to the 12 fourths. And 12 fourths reduces to 3. So this is the same as plus or minus 10 to the 3rd, which we know is 1,000. So b is plus or minus 1,000. Here's another exponential equation. See, the variable is in the exponent. E is just a number. E, even though it might look like a variable, is not a variable, it's just a number. So we're solving for this variable. We don't have the same base on both sides, so this is where logarithms are going to come into play. We start by dividing both sides by 6. And then we're going to take the log of both sides. And because we're using base e here, let's use log base e. And remember, log base e is the natural log. So natural log of the left equals natural log of the right. Now the natural log and the e are inverses. They're going to cancel, leaving you with just negative 4t. So negative 4t equals natural log of 1/3. Divide both sides by negative 4 and we'll have t by itself. So we have natural log of 1/3 over negative 4. I will leave it like that. There are other ways that a person could keep going and simplify. For example, natural log of 1/3 is the same as natural log of 1 minus natural log of 3. Natural log of 1 is just 0, because e to the 0 power would give you 1. So what we actually have is negative natural log 3 over negative 4, so the answer could be written like this, natural log 3 over 4. That would look a little bit simpler, but it took a lot of work to get something simplified. Sometimes it's not worth it. Especially in calculus, we don't spend as much time trying to simplify things as we might have before because we have bigger fish to fry. Okay, now we're going to solve a logarithmic equation, and I think this is going to be it. Yes, and we don't have a very long homework assignment, so if you're running out of time, don't worry, there won't be a ton of homework. Okay, so notice we have a log plus a log. We're going to try to combine these together. Before we can combine them, we have to bring this 3 up and make it a power. So we have log base 3 of y plus log base 3 of y to the 6th equals 14. Now if you have a log plus a log, you use the product property of logarithms, multiply those together. We have log base 3 of y to the 7th equals 14. Okay, from here, there are a couple of options. Remember what logarithms mean. You have your base 3, you raise it to the 14th power, and that's going to give you y to the 7th. 3 to the 14th equals y to the 7th. The other option is to exponentiate and just do 3 raised to the left side equals 3 raised to the right side. Oops, that's not a 3. Apparently I don't know my letters and my numbers. Sorry. I've got E on the brain. How about 3 raised to the left side equals 3 raised to the right side? That will get you to the same place eventually as what I wrote already. Okay, so we want y. We don't want y to the 7th, we want y. Let's take the 7th root of both sides. And this is the same as having 3 to the 14 sevenths. That would be the same as 3 squared. And 3 squared is 9, so y is 9. Okay, I feel like in the midst of doing all of these log and exponent properties, we're also kind of getting a chance to review some other things too, like rational exponents. So, you have a few problems to do that have to do with inverses and things being invertible, and then you have some problems to do, including this set right here, which has to do with log properties, exponent properties, and what we spent the majority of our time practicing today. Thanks, everybody.